Hi, welcome to Neural Search Talks by Zeta Alpha. In this episode, we have on the show Ash Vardanian, the founder of Unum, a very exciting library of high performance and large scale computer infrastructure for AI and search and database. Welcome on the show, Ash. Um,
Glad to be here. Thanks for inviting.
maybe to get started, how did you kind of roll into starting Unum, and how did it develop initially? Because you guys have been going for quite a while, right?
Yeah, we've been around for like almost 8.5 years now. Hard to imagine. Uh, we've I've had previous life in developing more like software applications and services of different kinds, and then I moved into science. And at some point, I realized that artificial intelligence is going to be the main force of the 21st century. And I thought I'd want to devote my life towards like advancing artificial general intelligence. And everyone has like their own vision of how we get there. I don't know what AGI will look like. I just know what kind of problems I'm best equipped to solve to get us closer there as an industry. So I started working on some of those issues. Many of them are about large-scale data processing, more efficient infrastructure, and that's how Unum began.
And so Unum is not a company, but more like a collective or a project. Can you describe a little bit the dynamics of that?
Yeah, so there are companies who very clearly classify themselves as like for profit or non-profit, commercial ones or startups, collectives or something else. I don't really differentiate structures that well. Uh, but at this point, I would just like describe us as a group of people who are working on some of the most advanced libraries for large-scale data processing being used across the industry despite our fairly young age for the world of infrastructure.
Funny that you say you don't describe structure so well for somebody who does such a amazing job at implementing structures in a very tedious low-level code as well.
Yeah, thank you. That's very kind.
So maybe you can explain to our audience what Unum actually does. What
Sure.
is sort of the philosophy behind the libraries, and what are the different components of your vision, and how do they play together?
Sure. So I think we had a few principles, core principles from the very first day of Unum. One of them was that modern computers are far more capable than the software that we use on daily basis. So most of the software is only taking like and consuming only like half or like quarter or 10% of the hardware's potential. And the second part of the story was that in a lot of those workloads, it's not just like the computing that has to be efficient, it's also the I/O operations that have to be optimized. And I/O is often about memory, external memory, or random access memory. So this naturally led us towards like a domain of problems, many of which are in search, that we started solving and designed several search engines over the years. So Unum designs, among other things, vector search engines, vector math libraries, uh, representation learning systems, and multimodal embedding models that can be also used for search, as well as networking libraries to serve the search results, and even storage drivers to fetch the data efficiently. So as you see, this is a fairly broad coverage, and as a person very intimate with search yourself, you understand that search is like such a vast domain that tackling it from one side is very complicated. It often makes sense just like to look at the whole picture and optimize it kind of simultaneously.
Right. It sounds a little bit like the whole shebang, basically.
Yeah,
And let me take a guess what the name Unum means.
go for it.
No, you tell me.
Oh, okay. So Unum in Latin means unity. So like one framework to build all of the advanced AI infrastructure, at least the one that we use internally for our work. But it also refers to some other interesting project called Universal Numbers, which is an alternative to the IEEE standard for the floating point representation in the modern computers. So the IEEE consortium has like a few standardized floating point representations, float 32, float 64, float 16, but there is a very little known alternative called Unum. So that's kind of the story behind our name.
Right. So two sides of two faces of the big puzzle.
Yeah.
How to efficiently implement it in modern hardware using floating point representations that are efficient, and the one infrastructure to rule them all, perhaps.
Yes, hopefully.
And one of the things that caught my attention with LLMs and retrieval augmented generation. Almost every developer in the industry is kind of saying, well, if you do retrieval augmented generation, you need to have vector search, right?
Yeah.
Having been in the search industry for like last 30 years, I've certainly see the charm and the potential of vector search, but it's not kind of the silver bullet. But still, has been quite a kind of explosion of vector search approaches. And you've also launched one of them, Usearch, kind of one of the components of the Unum ecosystem.
Yeah.
Can you tell a little bit why you did that with so many things already being around, and what differentiates Usearch from some of the other vector search or vector databases?
Sure. So first of all, I'm not sure the world has ever seen a vector database. We love the concept ourselves, but we are not sure that even a single vector database exists. So that's a separate topic for a long discussion. But there's definitely several vector search engines, and there are several databases with vector search capabilities using those engines. So this form of symbiosis is definitely not new. When we started working on Unum, search was like one of the essential problems that we were solving, so much so that implementing an efficient HNSW index structure was one of the interview questions for hiring engineers into the team. So and myself, I wrote like maybe 15 vector search engines over my career. And finally, a year ago, when the topic suddenly became attractive to researchers worldwide, I looked up a few implementations on GitHub, and all of them had their advantages and disadvantages. My first intuition every time is like, oh, maybe there's a way I can make this more scalable, make it work even faster. And oftentimes this works out, not always on the first attempt. Sometimes I spend like 8 iterations improving somebody's code base until I get some meaningful results, meaningful improvements. But with vector search, specifically in the Usearch case, we kind of unintentionally solved a few more problems that industry was facing. One of them was portability. So as it often happens in the world of machine learning, the core implementation is written in C++, but most of the practitioners would be using Python. So we have like this two-layer approach, having the core engine in C++ and the bindings in Python for the engine. This is how Thais is designed, Facebook's vector search library, exceptionally popular. Also implementing several indexing structures and quantization schemes, including the HNSW index, hierarchical navigable small world graphs.
Yeah, I think they kind of popularized it to the larger audience in a couple of years ago,
Exactly.
right?
But as you also know, there are two reference implementations. There's the NMS lib and the HNSW lib. So one is for the flat indices and the other one is for hierarchical structures. So I noticed a couple of places where an improvement can be made. over the baseline. One of them is about just using hardware capabilities better. So modern computers have this feature, SIMD, single instruction, multiple data, that kind of suddenly became popular in the last couple of years. It speaks to the ability of a modern CPU to process multiple pieces of information at once in a single CPU clock cycle. So instead of like comparing or like multiplying two floating point numbers while computing the dot product between two vectors, an essential operation in vector search, instead of that, using SIMD instructions, you can process like 8 entries at a time.
Yeah, it's like a mini GPU inside your CPU, right?
Exactly, inside every CPU core. So like, it's like multiprocessing at a level of a single core. But believe it or not, most compilers don't know how to generate those assembly instructions. So modern x86 instruction set is like in thousands of instructions. When I disassemble most of the stuff, that is most of the binaries that are compiled by recent GCC or LLVM, only like rare sections of code have been successfully vectorized with this SIMD instructions.
Right.
So there's still a lot of need for people who can write assembly for these kinds of kernels. And in cases of most search libraries, like including Face, which powers a lot of search workloads worldwide, most of the time people would just use BLAS, which is the basic linear algebra subprograms or subroutines, a
That
very
goes
old.
that goes way back, back to Fortran, if I remember.
Exactly. Yeah, it's like a super old standard.
Yeah.
It's been redefined in several programming languages. It defines the vector-vector, vector matrix, and matrix-matrix operations. And assuming we've had the experience of implementing those libraries and the kernels for all kinds of hardware, all kinds of CPUs, all kinds of GPUs, in our open source work, we follow the same tradition. If we need to make search scalable, let's implement those assembly instructions. Let's invoke them ourselves without letting the compiler mess this up. So we've implemented all the most common similarity functions for every recent version of a CPU, including ARM Neon, ARM SVE. SVE are the instructions available on AWS Graviton chips, on the upcoming NVIDIA Grace CPUs, on the upcoming Microsoft Cobalt. We also support 4 generations of Intel CPUs, including x86, Haswell, Skylake, Ice Lake, and Sapphire Rapids. So this is a lot of handwritten trickery, like hundreds of kernels.
Yeah.
But that's just one part of the puzzle. Another piece that came handy was that we always love to see people build search into applications across mobile, on edge, in different databases, not just in machine learning or data scientific pipeline. So for Usearch, the first weekend, I actually like implemented the first version overnight, or like maybe in 2 days. And in those 2 days, I implemented the bindings for the first 4 programming languages. So the core is C++11. There is a binding to C99, to Rust, JavaScript, and Python. All those 4 were available on the first release. And then over time, we've also added support for TypeScript, which was kind of obvious, Objective-C and Swift. We've added Java, we've added Golang, we've added C#. There's also like partial support for Wolfram, and I guess the list goes on. So we occasionally see people who use our libraries in the most unexpected places. Like oftentimes I would just meet a publisher of some iOS app randomly, and I would use that app on my own phone. And then I would realize that some of our libraries are powering search in all of those applications.
And maybe to get back a little bit to your HNSW implementation, and I mean, I think most vector search engines today use that as a core workhorse for approximate nearest neighbor search. So how can you characterize with the advantages in terms of speed or indexing time or scalability of your implementation?
Oh, sure. So you know how they say it, like there's the truth, there's the lie, and there's benchmarks.
Right.
So search is such a diverse topic that no matter
And
what
then
kind of
there's
numbers.
ANN benchmarks.
Oh yeah, in search there are so many things, so many variables that having one definite answer of like what works best uh, is kind of impossible. I
But
can
still,
share.
try to summarize like what would be your Steve Jobs pitch for how much better your
Oh, okay. I need to change and like I need to get like a black sweater and jeans to have like a proper Steve Jobs experience, but uh, trying to get into the mood. In the past year, we've reimagined everything about search. Now search is faster, lighter, easier to use. Uh, and when you compare it to most commonly used alternatives, I guess Steve Jobs doesn't like naming the specific projects or specific competitors. Uh, you will get the most advantage at scale. So honestly, when you deal with like a million entries or like a couple million vectors or something like that, I realize that oftentimes just pure brute force is more than enough for most companies.
yeah.
But when you start going beyond that, when you have tens of millions of entries, you can plot those curves of throughput versus recall. When we plot our curves against face and their default HNSW implementation, we oftentimes realize that we perform much better, A, at larger scale as in larger number of points, and B, at larger scale when you have more CPU cores. So implementing efficient synchronization between CPU cores is tricky. That's why the more cores you have, the worse phase will scale, most likely. Uh, in our case, in some of the last benchmarks we did with other like industry leaders, we've noticed that the break-even point in some of those benchmarks against face was about 30 million entries. So until 30 million entries, we were comparable in throughput. Maybe even face was faster. After 30 million entries, we take the lead. At 100 million entries, depending on parameters, we can be 10 times faster. At billion entries, we can be tens of times, maybe, I don't know, 100 times in specific cases faster than face. So the bigger you go, the bigger the advantages.
Right. And so a lot of that is due to this very sort of tight hardware optimization, knowing how the cores work, how the instruction sets work, how the
Yeah.
cache structure is. Um, how does that go for flexibility, right? Like you see, for example, like new embedding models are coming out, well, essentially every week. Um, on some of the benchmarks, the really large models have taken a lead, right? Like the
Yeah.
Mistral based embedding models that now have, very high dimensional, dense vectors coming out of them. Does that play well with this kind of tightly optimized uh, infrastructure?
I think yes, if you think about architecture deep enough. So in many ways, all of us, our entire industry, is standing on the shoulders of giants. And one of the features that is based on those giants in Usearch is called JIT compilation, just-in-time compilation. So it's a common trick in databases to precompile the query, like to compile it just in time, and then execute it as like a precompiled binary instead of evaluating some domain-specific language eagerly. In Usearch, I'm not sure, I haven't double checked, but it might be the case that we are the only vector search engine that supports JIT compiled metrics. So what essentially this means, you can have arbitrary vectors and you can define a callback, even in Numba, and Numba will use LLVM, one of these giant compilers, to compile a metric specific to your use case, to your number of dimensions, to your data type, and inject that precompiled piece of assembly into Usearch. And that's not even the only way. So oftentimes, when people treat this as just a one-off project. They integrate LLVM and they call it a day, which is probably fine. But we wanted to break things a bit. We wanted to see how far we can push like this JIT compilation and assembly injections. So we've documented two more approaches of combining the precompiled Usearch engine with custom metrics. The first one of them is Numba, which is a Python package using the LLVM compiler. And you use it to define your kernel in Python and inject that Python code into the C++ engine. The second approach is called CPPYY. It's even less known than Numba. It's a Python package that wraps around Cling, and Cling is a JIT compiler based on Clang, designed at CERN, the physics project, whose idea was essentially like, let's use C++ in Jupyter notebooks. And for that, we need some form of like evaluation loop for C++ code. So we've implemented this where you can define your kernels in C++ code sections within a Python source file and inject it down. And last but not the least, the Frankenstein monster of all is using a package by another friend of ours, Marat, who's designed Peach Pie. It's an approach to write x86 assembly in Python. So you can directly write assembly within a Python file without using any third-party compilers and inject it into Usearch.
It's like a lasagna.
Exactly.
Layers and layers stacked, yeah.
Yes.
But then it works efficiently.
Yeah.
So one of the other sort of trends in the embedding space that we've seen recently is that the length of the embeddings is increasing for large models, but there's also a need for efficiency. So people have also started to work on kind of quantized embeddings, even quantizing down to like binary embeddings.
Yes.
And not that many. So Joe Bergam from Vespa, he was kind of having the day of his life because they support it already for a while, and most other search engines don't. How difficult would it be to do sort of efficient binary embeddings in Usearch?
Oh, it's supported from the day one.
Oh, really?
Yeah, of course. And like, so binary embeddings are not new. So I've been in computing for around 20 years and have been doing a lot of search for the last 10 years. And even 10 years ago when I started, not only binary embeddings were not new, but even full bit level binary neural networks were already well documented on Intel's website. And if it's documented on Intel's website 10 years ago, it's definitely not new. So
I think what's new is that it's working really well, right?
maybe, yeah.
That it's
So
kind of keeping the generalization performance in search
yeah.
very close to the dense float, like the full float representation embeddings.
Exactly. I feel like it just that us as an industry, we've been a bit maybe maniacal about like bird-like float embeddings, very heavy ones, and we've just like focused all of our R&D for a few years on those, and we kind of forgot about everything else. So even in those older papers, I remember that bit-level networks showed competitive performance against floating point networks, or like even the same for the representations, not the whole network. It's just that people kind of chose the path of lower friction. For us, not only the binary embeddings are natively supported from day one, but we also work a lot on embedding models. So we do not release any text models, but we find the problem of multimodal perception very attractive. So how do you do search across images, videos, text, and different languages, code, molecular structure, biological structures, graphs, whatever, point clouds.
Yeah.
So
I mean, that's the beauty of vector spaces, right? It's
yeah,
like the Rosetta Stone of semantics in some sense. You can compare anything to anything.
that's the holy grail. I don't feel like we're still there. So in 2019, there's been this paper or like the model, the clip from
Yeah.
OpenAI, contrastive
Yeah, I think
loss-based
that's a
models.
very popular and widely used multimodal model.
Yeah. Indeed, you're right. It's like the most popular approach for synchronizing separate vector spaces and aligning them against each other. We use them extensively in our own models as well. The models would be called Uform. They include both embedding models for texts and images like clip, but
Mhm.
also very small generative models, mostly for visual question answering, captioning, and very compact chat on device. So contrastive losses, I would say, are not very new either. So when you look back into the history of computing and some of the older computer science stuff, you start seeing those repetitive patterns. And one thing that contrastive losses remind me a lot is force-based graph layout algorithms. So the way contrastive loss is computed, you take similar objects and then you random sample other objects. You
Away from each
exactly.
other and closer to each other. Yeah.
Exactly. It's analogous like to defining a graph between those connected or similar objects and then repelling the objects that are not connected to each other. So contrastive loss is practically the reimplementation of force-based layout algorithms in graph drawing from 30, 40 years ago. It works well, but I think we can do better. So last year we as an industry, not us specifically, last year we released a few models that follow up on the work of OpenAI and subsequent ideas from Salesforce. So Salesforce released this paper called ALBF that showed a very data efficient approach to training multimodal perception. We later improved on this approach, and on several retrieval benchmarks, we trained a model that only saw 4 million data samples, but was competitive with Clip that has seen 400 million data samples. So there is a lot of space for improvement in data efficiency, both for the alignment of those separate vector spaces. There's also a lot of space for improvement for the size of those models and the quality of the output embeddings. In our case, there are currently 256 dimensions, at least the release we had last year. But I guess by the time your viewers look into this video, we'll have another model
Yeah,
and the
you
embeddings
told me you
there.
are about to release a new generation of those, right?
Yes, exactly. Like we about to have new embeddings models and new generative model as well. So to give you a sneak peek or some of the interesting findings, in our new models, we'll have like some very small encoders, and the embeddings are also trained with Matryoshka-like approaches. So you will have multimodal embeddings for text and images in 64 dimensions. Very, very small. Aside from this, architecturally, we've noticed like a couple of really nice ideas in the papers of the last couple of years. Of course, it's not every idea that works. You kind of test 50 ideas, one of them sticks. We've noticed that the paper about using separate tokens as registers for vision transformers was a really good finding, especially for larger vision towers. On the generative side, we've noticed that if you curate the DPO datasets well enough on small models, you can win huge with even a very small sample of DPO stuff. So our previous models sometimes would already do question answering better than Gemini. And those last models had a decoder that is only 500 million parameters. Gemini is a trillion plus parameter model. So if you can do better visual question answering with a model that has only like a 500 million parameter decoder than a trillion scale model, that's already quite good. But with a good DPO data set, we managed to win another 200 MMLU points, which was an insane and unexpected result for us.
That's very cool. I guess it pays off sometimes to be a little bit GPU poor, right?
Yeah.
Um, So if you looking at that sort of fit of these models and the corresponding scaling infrastructure to modern hardware, I mean, we've just seen last week the announcement of Blackwell from NVIDIA. So they're just going bigger and bigger and bigger.
Yeah.
I think 1,000 watts for a single GPU. That's pretty radical. I think they're still able to sell it as somewhat of an energy saving versus compute. But where do you see this sort of evolution of hardware with software going in the next year or so?
I think we'll see a lot more chip companies popping up, some of them potentially dying or merging. So there is definitely a lot of activity in the market. Uh, a noticeable chunk of those new chip companies are focused on just one architecture, only a transformer. Some of them provide like compute for general purpose or like provide SDKs. Others just want to serve one model and do it well. I don't know which approach will win. In our case, we're kind of aiming to be general purpose, cross-platform, work on every machine. And I think we still have like a long way to go in terms of efficiency for AI models and their adoption. So our mindset is that for any kind of workload to go mainstream and large-scale data processing, you have to squeeze, let's say, 1 GB per second worth of throughput in whatever data processing you're doing. So if you look at existing BERT-like models, you can squeeze like 10,000 sequences per second, maybe 20, 30,000 sequences per second, and every sequence being, let's say, a kilobyte or so. This means only maybe 10, 20, 50, 100 megabytes per second worth of throughput per GPU, even on simple encoder-like models. So we still have like a 10x improvement ahead of us for this to be comparable to the throughput of our other systems, like the log parsing systems that we have, the traffic processing stuff, the databases, the search engines. A long way to go.
That's a very exciting picture because that basically means that a lot of that sort of exponential level progress will come our way almost by itself, right? If we just do the optimizations.
Yeah, probably. There's definitely some synergy between like co-designing software and hardware. I'm not sure many companies can afford that. But yeah, in our case, we'll be just adopting to whatever the best hardware is coming up. It's a bit of a maintenance hell, to be honest. So right now, we support more releases and more backends than most companies, I guess, or most packages, even in the Python ecosystem. So Usearch specifically has bindings to 10 programming languages. One of them is Python. And like our Python libraries, for example, oftentimes would have 105 binaries pre-compiled and released for every version of a package. For comparison, NumPy ships 35 builds per release. We do 105. So this means we aim to run on 64-bit machines, 32-bit machines, little endian, big endian, ARM, x86, RISC-V, you name it. And adopting to every new vendor coming up is a bit tricky, but it's nice to see that some of them find ways to communicate. Like one of the big concerns we had in the industry, for example, was the FP8 representation, because there's a IEEE standard for float 16, and even with that in mind, there has been like this brain float 16 format that came up a few years earlier and messed up a lot of like the hardware support for Intel and AMD. With FP8, now there is a vendor who's pushing two standards, NVIDIA, and Blackwell supports two FP8 formats natively. So we'll be looking into CPUs implementing the same stuff so that we don't have to have too many backends and we can just like focus on those two FP8 implementations.
Thanks. So that's kind of more on the technical side. I guess with Unum, you also have this kind of grander vision of infrastructure for very capable intelligent systems. Let's put it that way. What would be your sort of your hope for the development for those kind of systems coming into society at a large scale? Or do you say, I'm just I'm just a coder, don't bug me with that?
No, no, like I'm definitely a coder, but I love to imagine the potential impact of the work I'm doing. That's what wakes me up in the morning and makes me spend half of the day in this chair. So I think there's a lot of companies these days who look at the very basic applications of search, and that's great because there's always adoption curve. You start small with like some of the most obvious use cases, but uh, some of the most dearest use cases, at least to me, are a bit further into the future. So last year, one of the projects we've built, and I've shared it with you, Jakub, is called Usearch Molecules. It's one of the largest data sets of embeddings publicly available. It's 28 pre-computed embeddings for 7 billion small molecules that can be used for chemical research, for metamaterials, for drug discovery, and has been already used by several top-tier research labs around the globe and some of the pharma companies. News in science propagates slowly, but even assuming like this data set is less than half a year old, we've already seen some insane adoption. Now we're working on several other applications of our technology across natural sciences. And the biggest impact I see is not even us being able to search for products that we want to buy, but 10, 20, 30 years down the road, having personalized medical treatment, prolonging a healthy lifestyle for individuals around the globe, prolonging productive lifspan, with humans living not like 60, 70 productive years, but maybe like 100 productive years, still being in perfect shape to play with their grandkids and grandkids. This is the vision towards which we want to work, and search will be a huge part of it.
I think that's a great vision, Ash. And so thank you for being on the Neural Search Talks show. And I wish you a lot of success in achieving that vision in your 100-year productive life.
That goes both ways. I'm sure this is not the last discussions we're having around this topic.
Thank you.